Squeeze a handful of wet sand, and it holds its shape for about a second. Then it slumps. It runs out between your fingers. It behaves less like ground and more like a thick liquid that hasn't decided what it is yet. Now scale that up. 94 million cubic meters of it. Enough material to build more than 30 Great Pyramids. Sucked off the floor of the Persian Gulf. Sprayed into shallow water off the coast of Dubai. Piled up until it broke the surface. And then a city put on top. Apartment towers, hotels, a monorail, roads, sewers, power cables, water mains, tens of thousands of people, millions of tons of concrete, all of it resting on material that, a few years earlier, was loose sediment lying underwater. There is no bedrock under that fill. There is no natural stone shelf holding it up. Underneath the whole thing is sand sitting on more sand. Sand shifts, sand settles. And under the right conditions, wet sand can stop behaving like a solid altogether and start behaving like a fluid, taking everything above it down with it. Palm Jumeirah has now carried a full working city for close to 20 years. So why isn't it sinking? The site is where the trouble starts. The water off that stretch of the Dubai coast is shallow, around 10 or 11 meters deep where the island sits. That shallowness is the only reason the project was affordable at all. You cannot fill an ocean, you can fill a shelf, but shallow water hides something inconvenient. The seabed down there is not a clean sheet of stone. It is loose sediment, sand laid down grain by grain over thousands of years, never squeezed, never crushed under glaciers or mountains, never given the geological time that turns sediment into competent ground. Engineers have a term for that condition, normally consolidated, which means, in plain language, as loose as it has ever been. That seabed has never carried a serious load in its existence, so nobody could say with confidence how it would behave the first time it was asked to. And the plan was to place 94 million cubic meters of even looser sand on top of it. Sit with that for a moment. They weren't building a foundation, they were building a problem, and then asking the problem to hold up a skyline. There was a second complication, and it catches almost everyone off guard. Dubai sits at the edge of one of the largest sand deserts on Earth. Sand everywhere, free, right there, useless. Desert sand has spent thousands of years being thrown around by wind, grain against grain, tumbling and grinding until every particle is worn smooth and round. Pour billions of those together, and they roll over one another like microscopic ball bearings. They don't interlock. They don't grip. Desert sand builds beautiful dunes precisely because it flows so easily, which is the last property you want underneath a tower block. Marine sand is a different material. Grains that have sat on a seabed keep rougher, more angular edges. Angular grains bite into each other, put them under load, and they wedge instead of rolling. The sand around Dubai is also calcareous, built largely from broken shell and coral fragments, which brings its own quirks, but it has the texture construction needs, so the material had to come from the sea, dredged from borrow areas several nautical miles offshore, hauled back, and placed exactly where the drawings said, which raises a strange practical question. How do you place sand accurately at a specific point when there is no land there yet? No survey pegs, no corners, no reference points at all, just open water and a ship that is constantly drifting. The answer came from orbit. The dredging fleet worked on differential GPS, satellite positioning, corrected by fixed stations on shore, which cancels out most of the error in the raw signal and pulls accuracy down to the scale of centimeters instead of meters. The vessels knew their position on open water to within roughly the width of a hand. The island existed as a digital model. The crews were effectively painting a shape onto the sea using coordinates. The delivery method has a name that sounds far too gentle for what it actually is: rainbowing. A dredger fills its hopper with a slurry of sand and seawater, holds position, and fires that slurry out of a bow nozzle in a high, wide arc. Thousands of tons of sand thrown through the air, falling in a curtain onto the growing island. Below the waterline, sand was pumped and bottom dumped. Above the waterline, roughly the top 3 meters was built by rainbowing, because a ship can throw sand into places a ship cannot physically reach. Frond by frond, the shape rose out of the sea. 17 fronds, a central trunk, a layout chosen because branching maximizes shoreline and Dubai had run out of coast. By October 2003, the reclamation was essentially finished. Around 5.5 square kilometers of new land where there had been open water, and at that moment, it was almost entirely useless. They had made land, they had not made ground. That distinction is the whole story. When sand is placed hydraulically, pumped and sprayed through water, the grains never settle into an efficient arrangement. They drift down and land wherever they land, forming an open skeleton riddled with voids. Every one of those voids is full of seawater. Fresh hydraulic fill sits at the loose end of the density scale, open, compressible, waiting. That creates two separate threats, and they work on completely different timescales. The slow one is settlement. Load a loose granular mass, and the grains gradually shuffle into tighter packing. The surface drops, centimeters, sometimes more. If it happened evenly across the whole island, you could almost design around it. It never happens evenly. The fill is deeper in some places than others. The seabed underneath varies. The weight on top varies enormously between a villa and a hotel. So one corner of a structure goes down further than the other, and that is differential settlement, which is what cracks walls, shears buried pipes, tilts floors, and splits roads. The Leaning Tower of Pisa is the most photographed example on the planet. The fast threat is uglier. Loose, saturated sand, shaken hard enough, can lose most of its strength in seconds. The shaking makes the grains try to compact, but the water trapped between them cannot escape quickly enough. Pressure in that trapped water spikes and pushes the grains apart until they are no longer pressing firmly against each other. At that instant, the ground stops transferring load through solid contact. It behaves like a heavy fluid. That is liquefaction. Buildings tilt into it. Buried tanks float up out of it. And it doesn't require a catastrophic earthquake. Moderate shaking will do it, if the sand is loose enough and wet enough. Dubai is not sitting on a major fault line, but the region has enough seismic activity that designers are required to take ground motion seriously. So, an island made entirely of loose, water-saturated, freshly placed fill, with a city scheduled to arrive on it. Nature does have a solution to this. Sediment compresses under its own weight over time, cements slightly, and slowly becomes competent ground. That process takes thousands of years. For genuinely strong material, millions. The developer had until 2006. So how do you buy geological time? You stop waiting for the ground to settle. You force it to settle, on your schedule, while there is still nothing standing on it. The technique is called vibrocompaction, and once you see how it works, the mystery of this island starts to dissolve. Picture a steel probe several meters long and about 40 centimeters across. Inside it, eccentric weights spin on a shaft, making the whole thing shudder sideways at high frequency. A crane holds it vertical above the sand. Water jets at the tip fire downwards, fluidizing the sand directly beneath, so the probe sinks under its own weight, driving down through the fill to the design depth. On Palm Jumeirah, that was typically around 10 to 12 meters, close to the full thickness of the reclamation. Then, the real work happens on the way back up. The vibrating probe pumps energy into the sand around it. For a radius of a couple of meters, the grains are shaken free of each other, and gravity does the rest. Released from friction, every grain slides into the nearest available gap. The loose skeleton collapses inward into a tighter, denser packing. Water is squeezed out and up. The probe is lifted in stages, compacting a column of ground as it withdraws, and something visible happens at the surface. A crater forms. The ground around the probe drops away. On reclamation work of this kind, treated surfaces can settle on the order of a meter as the fill densifies. That crater is the entire point. That settlement is the settlement that would otherwise have arrived years later, slowly, unevenly, underneath somebody's home. Instead, it happens now, in daylight, with nothing on top of it. The crater is backfilled with more sand. The rig moves to the next point, then the next, and the next. The probes worked across a tight grid, with reported spacing on the order of 2.5 to 3.5 meters between treatment points. Across 5.5 square kilometers, that means an enormous number of insertions, carried out by a fleet of rigs running simultaneously for months, from 2004 onwards. Contractors on the Dubai Palm program have described treating well over 100 million cubic meters of fill. The method has a blind spot, and the engineers knew about it. The top couple of meters never densify properly because there isn't enough confining pressure up there for the process to work. So the surface was finished separately, with heavy rollers and impact compaction, building the crust that roads and shallow foundations would actually sit on. Where testing showed the treatment had underperformed, usually because a pocket of fill contained too much fine silt and vibrocompaction only works reliably in clean sands, the answer was to go back and treat it again, or to install stone columns instead. Gravel shafts rammed down into the fill, which stiffen the ground and give trapped water a fast route to escape. None of this was taken on trust. Verification ran continuously, with cone penetration tests pushed down into the treated fill, measuring resistance meter by meter, mapping the strength of ground that had not existed 3 years earlier. According to the developer, the finished result had a bearing capacity in the region of 150 kilonewtons per square meter, roughly 15 tons of load spread over every square meter of surface. At the time, that was described as around double the typical capacity of the natural ground on the mainland nearby, which is the quiet punchline of this entire project. They took the weakest material on the site and turned it into ground stronger than the coast it was built beside. And that is what the phrase "sand into steel" actually means. Nothing was chemically transformed. Not a single grain became metal. What changed was arrangement. The geometry of how billions of particles touch one another. Grains that used to roll apart were rearranged into a dense, interlocked mass that carries load through solid contact instead of through trapped water. Same sand, completely different behavior. Nobody defeated the material, they reorganized it. But dense ground is only half of the structural answer, because compacted fill is still not bedrock. For most of the island, that doesn't matter. Villas, low-rise blocks, roads, the general fabric of the place. Spread footings and raft foundations distribute those loads over a wide area, and improved ground carries them comfortably. Tall buildings are a different equation. Concentrate thousands of tons onto a small footprint, and you have to reach past the fill entirely, into the older, stronger material beneath it. That means deep foundations, piles bored or driven down through the reclamation and seated in competent strata below, so the weight of the building skips the man-made ground completely and lands on geology. And that ground fights back in a way that has nothing to do with settlement. The water table sits close to the surface, and it is seawater. Chloride attacks the steel reinforcement inside concrete. Sulfates attack the concrete itself. In the Gulf, marine foundation concrete has to be specified defensively. Dense, low permeability mixes, generous cover over the reinforcement, sulfate-resisting cements. Get that wrong, and nothing sinks. It corrodes quietly from the inside, and the bill arrives decades later. Now pull back, because there is an attack coming from a direction we haven't touched yet. Water. An unprotected sand island in open water has no long-term future. Waves would chew into the fronds. Currents would drag the material sideways along the coast and redistribute it. The palm shape would blur, then smear, then disappear. That is what the crescent is for. 11 kilometers of breakwater wrapped around the outside. From the air, it reads as a design flourish. It is the only reason the island still has an outline. Structurally, it is a rubble mound. A sand core built up off the seabed, a layer of smaller rock over that, and an outer armor layer of individually positioned rock, with the largest pieces weighing several tons each. Somewhere in the region of 7 million tons of rock in total, quarried inland and barged out. Its shape does the work. A vertical wall takes the full punch of a wave and reflects the energy straight back. A sloped, rough, porous rock face makes waves break early and run up the slope, bleeding their energy into turbulence and friction between stones. The crescent stands only a few meters above sea level, and it does not need to be higher because the Gulf is small, shallow, and enclosed. Waves need open distance and depth to grow large, and here they have neither. The engineers were designing against a comparatively well-behaved sea, and they sized the structure to match. Then the crescent created a problem nobody had ranked highly enough. It was originally conceived as an unbroken barrier, and it worked. It kept the waves out, and it kept the water in. Inside the ring, circulation collapsed. The water between the fronds went still. Still, shallow, warm water in that climate loses oxygen, accumulates nutrients, and turns stagnant. An island being sold on its beaches was heading towards water quality that nobody would want to swim in. The fix was to cut the crescent open. Gaps were introduced so tidal flow could move through the enclosure and flush it out, with reported exchange times inside the breakwater on the order of a couple of weeks. It is a revealing moment in the project. The structural engineering had been modeled to exhaustion. The behavior of the trapped water was the thing that had to be corrected after construction had started. On projects this large, the failure that catches you is rarely the one you were watching. So is the island perfectly stable? No. And the honest answer is more interesting than a clean yes. Satellite radar surveys of the island have detected ongoing ground movement, with reported rates of a few millimeters a year in places. The developer has disputed those interpretations. Both positions can hold at once. Satellite interferometry measures surface movement extremely sensitively, and slow residual settlement in deep reclaimed fill is expected behavior rather than evidence of failure. What matters structurally is not whether the ground moves. It is whether it moves unevenly, faster than the design allowed, under something that cannot tolerate it. The upkeep is real too. Beaches on a man-made island are not self-sustaining. Sand migrates, and it has to be put back, with major replenishment campaigns moving more than 1 million cubic meters at a time. Rock revetments need repair. Palm Jumeirah is not a finished object. It is a managed system, and the managing never stops. The limits are worth stating plainly as well. Vibrocompaction only works in clean, granular soils. Try it in clay, and it achieves almost nothing. Every technique here depended on gifts specific to this location. Shallow water, a mild wave climate, abundant suitable marine sand nearby, quarries within barge distance. Remove any one of those, and the economics fail long before the engineering does. The follow-up islands make the point. Palm Jumeirah was largely reclaimed and then stopped after the financial crisis of 2008, sitting untouched for well over a decade before being relaunched in 2023. What stalled it was never the soil mechanics. The ground improvement worked, the funding didn't. So, finally, why isn't Palm Jumeirah sinking? Because it already did. That is the answer. The settlement everyone imagines waiting somewhere in the future was deliberately pulled forward and extracted in advance, driven out of the ground by thousands of vibrating probes, hole by hole, crater by crater, across 5.5 square kilometers, before a single building went up. The island dropped while it was empty, on purpose, under supervision. What sits beneath the city today is fill that has already done most of its collapsing. Add a breakwater that strips out the wave energy which would otherwise erode it. Add deep foundations that carry the heaviest loads straight past the fill. Add testing, monitoring, and maintenance that never finishes. There is no trick in any of that. There is no hidden slab of concrete buried under Palm Jumeirah. There is only sand. The same material that ran out through your fingers at the start of this, rearranged into an arrangement that behaves like something far stronger than it has any natural right to be. And that is the part worth holding on to. This was never a story about conquering nature. Nobody beat the sea, and nobody beat the sand. What engineers did was quieter, and honestly, harder. They understood the material well enough to bargain with it. They worked out precisely how the ground wanted to fail, and then made it fail early, cheaply, and on their terms, so that it would not fail later, on somebody else's. Every solid piece of ground you have ever stood on went through some version of that process. The difference is that the planet usually takes a few million years, and nobody is standing there watching. Here, it took about 2.